All right, just before the break, we talked about the details of the assignment. All you need to do is I will provide you the CAD 2D drawing, something like this, okay? And based on this, you need to draw a CAD model and then the FEA mesh. All you need to do is to make sure that at least 30% of the mass reduction. Then you have to make sure the factor of safety is between 2 and 3. Then you have to make sure that the vertical displacement should not be more than 0.5 mm. And then we need to check the strength, that the von Mises stress should not be more than half of this. All right. Okay, I'm going on this now. All right, make sure that you do not sleep. Okay, so when you open this file, all right, stop doing it, whatever you are doing. Just look at it over here, and then I'll give you the time. When you open the Fusion file, so you can see it's like a blank option over here. Then you have multiple options to draw. So you can draw any sketch. When you draw the sketch, so you can see it over here, the origin, the X, Y, and Z direction. So something is called front, back, and different views are available. We are going to make a sketch over here. Okay, so you can make a very simple sketch, something like this. Okay, and then you can modify it a little bit if you want. For example, if you want to create an arc, you can create 3-point arc, some other arc. You can see it over here, the drawing. So in the CAD model, you can draw it by dimensions. You can also draw it by constraints. Okay, so you can give it some constraints to it. For example, it automatically makes some constraint. You can see equal to over here, which means the length of this line and this line is same. You can see the tangent, sorry, normal 90-degree sign over here. So when I give it to you, these sort of things, okay, so I put the constraint sign as well, only the tangential constraint. So just to make sure that this line, this circle, do we have this tangent relationship?
Yes.
You can provide this tangent, this line. Okay. You can see this constraint sign? So in the drawing also you probably can. You can make some circles, okay? You can also make small circles here. Okay. And then you can give these circles constraint that they all should be equal to each other. Okay. So when I change the dimension of one, every one will be changed. You can make auto constraints. You can put except this auto constraint, and then maybe give the values which make more sense. Let's assume that this is the drawing, because our purpose is not to present or spend too much time on the. Just let me make one more change. Okay, some part of it is not constrained, but it's okay. Then you can take the extrude command, like this is sketch, okay. And then you can do it by just dragging it or just give the value. Okay, so a CAD model is ready. So when I'll give you these sketches, you have to draw this. So you can see it won't take more time. Any question? Yeah.
Should be the right if you want in the top phase or it should be in the right?
It doesn't matter because it's a top phase, bottom phase, sideways, this orientation or that orientation. It does not. It's just a space. Okay, and every time when I solve theories in the class, I say material has no sense of orientation. This orientation is your choice. If you put it on the other face, just make sure that the load is applied in this direction. If you make it in this plane, the load is applied in this direction. And because it's in a space, you can view it like that, you can view it like that. Okay? Just to be consistent with the rest of the procedure, I made it on this particular. Okay, once we do this thing, then you can go to the simulation. And what is simulation? We talked about that. In the simulation, there are multiple options. We need to use two of them. Number one is static stress, because we are in the static failure. Okay, so we'll do the static stress. And number two is shape optimization. Once you learn these two, then you can go back to the other. They are very, very interesting things to do. Okay, let's start with the shape optimization. In your assignment, you have to do a few extra steps, which I'm not going to do, but everything is explained over here. When you bring your design, so you can see it over here on this top side of it. From design, it's become simulation. So for the simulation, you have target body because it's not an assembly, it's just a single part, so it's okay. The most important thing is the material. By default, it will take the steel. If you right click and look at the properties, it will give you all the properties, okay? And this is the yield strength of the material. If you want to solve it by some other material, be my guest, okay? You can do this thing. You can change the material and you can solve it with some other materials as well. As long as you are in those generic borderlines. What is that? 30% reduction, factor of safety 2 to 3, or whatever the material the on my should be, less than half of the. Okay, then in the shape optimization, you leave it by default, but you can also provide it some information. Right now you don't need it. Just leave it by default, everything, and then leave this these parts by default as well. But once you complete this assignment, then you can go and make modification. Then you can see there is a contact. Since we have a single part, there is no contact. Contact will come when there are two parts. Okay, one part, another part. They are in contact. Okay, so you probably need to define the contact over there. Since we have only single part, we don't need it. Then we have a mesh. Okay, we can produce the mesh now, or we can when we solve it. Okay, since we select the shape optimization, everything will be working. Now we need to give it some boundary condition. For each of you, the drawing, the boundary conditions are given. Sometime a flat face, sometime a. This one, let's assume these three holes are the. So first you go with this one, and you say structural constraints. I click on the structural constraints, and I click on this part. With the shift key lock, I can select multiple parts, and you can see it over here in all three directions. U is displacement, U direction, displacement in X direction, displacement in Y direction, displacement in Z direction is 0. What does it mean? It means that this is basically screwed in something, so we recreate the physical world in the simulation.
Yes.
Okay? But we are not putting the screws, but if you put the screw, we can do that analysis as well. But in that case, we have to define the contact and this and that, and this become a more complex problem. So this is just to define the constraint. When you define the constraint, you can see this lock sign over here. You can define, depending upon the drawing, this thing you cannot deviate, you have to follow what I said. For example, if your constraint is this surface only, you can define this surface. Okay, to that part, like it's glued something or some welding. When you define the constraint, the next step is to define the loads. So you can define different sort of loads. Define the load in this circle. Then there are different types of loading is available, normal to the plane, okay, angle at some angle. So it's also possible that that bracket is holding at 45 degrees some rope or something. Okay, so we can define the load in 45 degrees. But here we already define the load in the downward direction. So for the downward direction, you just come over here, the vector form, and you can see it over here. The y direction is upward. So depending upon your origin, which you can see it over here, you need to go to the vertical side, and I'll define it minus, y minus, because we want to have it downward. Positive is upward, 1.5. It's kilonewton, so you can change the units as well, but we don't need to change any unit. Now you can see the load is applied.
Yes.
So what we did up till now, we defined the constraint and we defined the, what is the second part we defined? Any question? Any problem? No. Yes.
When you constrain the small hole, the free hole,
Yes.
and it means if you constrain it in X, Y, Z direction, it means that there is no rotation.
No, it means it can rotate in that. But here you see that there is no rotation, so it will be constrained in that. Because there are 3 X, Y, Z, linear, and 3 rotation. Okay. So by default, when we say fixed, it blocks all 6.
Okay.
Okay. So these holes are basically blocked in all 6 possible rotations. If you want to define the pin, okay, there are other as well. And in your statics course, you learn about it. What is the fix? So you have X, Y, Z, the direction reaction. If it is a pin, it means it can go into one direction, but it can. Okay? Alright, we are good to go to solve it, but just before something, add you one more thing. This is called preserved regions. So when we are going to optimize, we can optimize it. This is very basic, simple problem, so we can optimize everywhere. But we want the software to tell the software that do not go in this area, do not optimize in this area. Leave this area as it is. Because maybe there are some other parts that are going to fix over there, maybe some other shaft, some bearing will come. So to hold that bearing, we need a minimum of that area, which is already minimally drawn over here. Let's assume. So in that case, we tell the software, do not optimize that part. So I leave it on you. You can select any of the part not to optimize and any of the part to optimize. But for this example, which I'm doing right now, I'll optimize this load area. Preserve this load area. I'll click on it. You can drag it a little bit so you can go up and down, because after that part there is nothing, so it doesn't matter. And then you can drag it in the other direction as well. When I do like this, everything which is under this so-called green region, the software will not tell you to reduce them. Okay?
Yes.
It's up to you. If you want to reduce it, you can do it. You can delete that part and solve it again. But for now, we say that it is not going to tell, although it can tell us, but it will keep that part and then optimize the other area.
So it is prevent just this area.
Just this area.
It will not do anything to it.
Yes, because it's preserved. Preserve means keep it as it is. Don't make any changes in it. The rest of the part, it's not going to change and it will do the change. But for the rest of the part, it will look at the load path, where the load is going.
Yes.
Where the load is not going, it will say, yeah, remove that area of the load. If that part is not sustaining in the load, why do you need to have that part? So that we can optimize it. This is our target for this problem. Okay. When we do this thing, we are almost good to go. Then we can do generate mesh. If you solve it, it automatically generate mesh. But just to show you what I said earlier on, this is the mesh. Okay?
Yes.
So each point, it will do only the calculation at this point, this point. Anything in between, it will do the interpolation. Later on, when we see the model, we will not see the mesh, we'll see the solid model. But basically, the values are only. If you look at it, there is some mesh report as well. It will tell you exactly how many elements in it, how many points in it, how many this. Okay? So you can find out exact number of it. So what I'm going to do, I'll show you where you can do the coarse and fine. So you start with the coarse one and then go for the fine one. The good thing about the Fusion 360, it will do all the calculations in the cloud. So if your laptop, desktop is not heavy enough, it doesn't matter. Okay, it's a licensed software. The license allow you to connect with the API. Okay, behind the API, there is a computer programs already written over there. It will process it over there and send it back to you. So your laptop will not heat it up, your desktop will not heat it up, your computer economy will not be utilized. But since it is a expansion over there, education license. So for example, ANSYS, it won't allow you to go more than 25,000 mesh size, 25,000 points on the mesh or elements. And for Fusion, I don't know exact value, but it will go to that. Okay, so you can go over here, edit it, and you can see it over here. You can give it an absolute size, you can give it a percentage. So let's say, right now, remember this picture?
Yes. Yes.
I'll try to reduce it a little bit. Okay. Because you change it, you have to regenerate it. When you regenerate it, now you see the mesh size is more dense. More dense and more fine, more refined. And now the computer will take more time because you are asking them to solve more data points. Okay, for this, it won't take much more time, but still I'll just do it with the okay, once we done, we go to the results. It can come from here or we can solve it from here. Result. Now it will tell us that it will tell how many, because you can solve multiple parts and then upload it, or you just say, okay, solve this simulation, start this study now. Since it's a new part, let me call this. All right, now it's going to add in the queue line where other people are also submitting their results, or the computer, I don't know where it is, to solve it. Okay, it won't usually take more than a minute or so hopefully. So what the computer may be doing right now?
Processing.
Yeah, processing of
Going point by point.
They take a point by point, they make a matrix, and they solve these matrix for the individual points. Okay. So the size of that matrix will become bigger and bigger and bigger. It's called stiffness matrix in the middle. Okay. So that if you have more points, you have a stiffness matrix bigger. If you have less points, the stiffness matrix is small. So once we get the results, it will go not only because we are in the optimize, remember, because we click it from the simulation, there are multiple options. We click it on what shape optimization, something like that. Okay. So it will work only on the load paths and check the load paths, how the loads are going because there are 3 holes which are sustaining everything, and there is one hole which has a sort of a load. All right, so it's ready. Close it, and now you can see. Here, you can see the mass ratio. Your target is to reduce more than 30%, and you can see it over here. And whatever the mass you can calculate it before of the CAD model, and it's telling you approximately this is the. I'll drag this legend, and you can see how the things will change. You need to observe it very carefully. See? All these, sort of this part is not contributing a lot in bearing the load. Why not? Because one of the problem with this problem is it's not symmetrical. The holes are here, and the load is a little bit away here. Okay. So when the load is not, if the 3 holes and the load is exactly in the center, then almost all the part will equally contribute. There's only some edges which you do not need it. But since it's not or in other words, it's sort of a eccentric load, so it will create a movement in the plate.
Yes.
Although it's a plane stress problem.
Yeah.
But from the hole point of view, it will create a movement because the holes and the load is not in the same direction or same line of force. Okay. So in that case, we have some redundant material. And this blue part is basically the redundant material. So if I come over here, like 69, okay, because we have to go above 30%, this will create, do the task. Okay. Let's go a little bit more. And you can see it over here. Although this part is in the red color, which means it has to be here. We already preserve it. If we do not preserve it, it will be there because it's a red color part. It is the most load-bearing part. We finish the results.
And we come over here.
In the results, we go to the promote. Now, what we are trying to do over here, we're trying to take this FEA optimized result to go into our design or CAD model. So once it go to the design, we have both parts, which we can see it on the, basically they are merged with each other. And we'll see it over there, okay, this part, we don't need a material, we'll remove the material. Okay?
So is that how we decide that the redundant material is going to go, or is it?
Yes. One way is, if you look at it, if you have a very good photogenic memory, you just memorize, okay, this part, you go there, but you don't know the exact dimensions. When we'll promote it, you have exactly copy paste over there and you can play around. So I'll see how we can. Let's go to the promote and this model into design process. Okay? Now you see over here. In our bodies, before that we have only one body, this one.
Yes.
And now we promoted another body, which is this one. But this is a meshed body, so it's not a physical body. So what we can do now? We open both of them and make another sketch. So what I'm trying to do over here is okay, so I roughly try to trace this path. Okay, there are some areas over here we can reduce it to, but let's see it for a while. We can do it. So this is
Excuse me, Dixon.
sorry.
In the symbol on the face. On the face. Yeah. Yes, you didn't select the.
We select only the outside sketch.
Yeah.
Okay. So what we can do, like if this is a very sharp edge, you can do the analysis and you can see this sharp edge will not be very good. I'll remove this one and make some little bit over here. Okay, this one is a very sharp edge too, but because it was a loading part, so just make a small. Okay, now it looks a little bit. We can go to the simulation again. It says that because of the shape change, the results are not reliable. It's okay. We are going to clone this thing. So this new will come over here. Okay, because we clone it. Cloning means just whatever the part, you make another part, like just like a file save as. But you are in the file and you just clone it. Okay, so you can see the constraints are there. This box sign, the load sign, this save part is there. And yeah, just solve it again. So for example, in your design, you don't be able to reach to the like 30% or more in the first go. So you can come over here, you can modify it, then you solve it again, and then you solve it again. So hopefully you're able to do it in the first go, but in case if it is not, then you need to repeat it a few times. This is not going to happen, but
We talk about the green region. That will be applied all the result about this region.
no, this region is preserved region. So when it calculates the load path, even if the load path is going over there, it says keep it.
Why you make it more than the radius of the circle? The optimization.
The green, why you make it
Why
bigger?
why?
It doesn't matter. Because if you just put it in the circle there is no material.
Yeah.
You have to go inside. The material is this plate. The material is this plate. This hole has nothing in it. Even if I make a green part as a whole, it's a useless activity. Because for the stress, you must have a area. Stress is inside the area. This is equal to not making it.
Oh, so I need to make it wider.
I don't know you need it or not, but you have to tell in the material. Okay? So if I just put it into the hole, in the hole there is no material. There is no load path in it. The load path is in the steel, which is the plate. Okay. This is an additional step. It's up to you if you want to do it. If you don't want to do it, it's okay. But just to tell you that you can preserve any area to be, for example, a part is statically there. And you want to keep that part. So put it. Or even don't put it, then later on you just don't remove it. Okay? Alright, the results are ready. Now you can see it over here. Okay. So this is 80% of that model. Okay, it may be more than that of the previous model. So you can, up to you, if you want to further reduce it, so you can do this thing. Okay. And rather than having a solid, you can make a hole in that plate. Remove this part, remove that part, join this hole with this three parts in a very good manner. Okay, let's say we are okay with this part. Go back to the. Let's go back to the design first. And then go back to the simulation.
Yesterday or not?
Okay, this time we are going to do the static stress analysis. Okay. So in the static stress analysis, maybe there are some other shortcuts to bring the same clone over there and then change it. I don't know. So we'll do again this constraint. Load. Remember the load is this direction, vertical direction. So because our vertical direction is y, upward positive, downward negative. So downward is 1 because it is fluid. Okay. Just make sure that the material is same. By default, it takes this material. Okay, we are not, it will do the match by itself. Just go and this. So you can use the same file, or you can file save as to next one, so that if you want to see the original one, you can go back to see the original. In this file also there is the option you can go revert in time and see the initial plate. But just to save it, you can file save it V1, V2, version 1, version 2. Now this time, before that it was doing some load path to see where the material is excessive. Okay. Now this time it's a whatever the material is there, what is the load condition? Okay. So these are the other two constraints we have. In fact, more three constraints. One was the factor of safety, another one was displacement, and the last one was strength. Okay. So we are going to change it, or see and verify it with the help of this static analysis. Okay?
But he is by default he is selected or I select?
What is selected?
The three, the factor of safety and the
No, no, no.
And the one who
It's a
chooses
Factor of safety, it will tell you what is the factor of safety of this material, this design, and this load.
this.
I'll show you shortly.
Yes.
All right, the results are ready. Okay. Go to the results. Since it works somewhere else, so it has to download. All right. So first thing first we got is the deformation. Okay. So you can see it is little bit less deformed. Before that it was circle or it's elliptical shape because it's a deformed shape. If you want, we can switch it back to the normal shape as well. But the most important thing over here you can see is, okay, we have to change these limits. So this one is 3 in our case, and minimum is 2. Okay, so everything is blue, like well above this. So I close the blue. So only this part, you can see this part is in range, while the rest of the part is above 3. So it's not acceptable.
Indicate what this blue color.
This is just a threshold. You can set the threshold anywhere.
Okay, but it what is shown?
It's not showing anything. These three colors are showing the blue color is above your above limit or maximum limit. The red color is below your range.
Yes.
And our range is 2 to 3. So green color is everything in 2 to 3.
Yeah.
Okay. If I switch off the red, the blue color and the green color, okay, so nothing is red over here, which is a good sign. Okay. So it means this analysis showed that still there is a huge potential to optimize it further. Okay, because the factor of safety is still very high. Okay. So these are the results. So you can see the factor of safety. Then we need to go to the displacement. This is the total displacement. Okay, when the load is applied, it's actually a little bit exaggerated, but this is how it will.
That's mean the skid there is safe in the safe region, right?
Sorry?
It will not deform with this load, right?
It will deform. It will deform exactly like this.
Ah.
This is a little bit more exaggerated.
Yes.
This is the total displacement. Okay? So it may deform in other direction. But we are interested only in the vertical displacement. Where is the vertical displacement? This direction. Because our x, you can see x, y, z. So it's negative y we are interested. So what we are going to do is to look at the y displacement. So you can see the minute, because it's a negative, so the negative values are, so because it says minimum, but basically this is the maximum, it's just a negative sign. So it's 0.019 millimeter. It's well within 0.5, so we don't need to worry about it. Okay?
Yeah.
This value, if it is 0.51, we need to be very worried about it. Because this is our constraint in the design, that the total displacement, not the total displacement, the displacement in the vertical direction should be less than 0.5 millimeter. You need to check the units all the time. Okay, so from factor of safety point of view, it is safe. The design is safe, but it's too safe.
Yeah.
Okay, so we have to repeat everything to make it sure that it goes within that range, between 2 to 3.
All the blue will go to the green range, or maybe around 80% of
No.
blue.
Yeah, that's very interesting question. I think, yeah, most of the parts should be in the between 2 to 3. Okay. If some parts, because there are some safe regions, which will definitely go to the factor of safety of 4 or 5 or something. But there should not be any part which is less than 2. There should not be any red part. When you optimize it, you'll see some red parts start appearing, especially near the hole. Okay, so you need to make sure that your optimization is such a level that majority of the part, when I say majority, it can be 80% or something. Because some regions are always safe, especially when you do this constraint. And these are the holes, so the constraints are a little bit far away. When you have a flat surface constraint, things are a little bit different, because you have a whole spectrum of constraints. Okay, the last thing which you need to see, so you can see stress in other direction, you know the principal stress and all these things, everything is a one mass. For this load, the one mass stress would look like this. Okay. So you'll see at some point the load will be very high. At some point the load will be very high. At this point the load is 70 megapascal. Okay. And what was the yield strength of the material?
Half multiplied by 207.
207. Okay, 207 divided by 2.
It may be
103. 3 something? Okay. This one is
Also the same.
70. Oh. So at least from the strength point of view,
Yes.
the boundary I define, you are within. Okay?
Yes.
So the strength point of view, this design is okay. From displacement point of view, this design is okay. From factor of safety point of view, this design is not okay because it is not fulfilling the criteria defined for this design. That is, the factor of safety should be between 2 and 3. From optimization point of view, in the first go, we made it more than 30%. In the second go, we can further reduce it as well. Okay? So you need to little bit do this. And this whole thing is so automated, you do not have to even use your brain. Just do the things mechanically, constrain mechanically, do this thing. And it will do it for you. What is your job? Your job is to make the engineering judgment at the end. Make sure that I define only 4 criteria here, that everything is within that criteria. This displacement and yield strength will always be there. Just this, more than, even in the first go, some drawings can go like 60-70%. But once you look at the factor of safety, maybe it's go below 2. Then you have to come back again, add, put it back the material, okay?
Yes.
And then it's, if this value of the von Mises, what is von Mises? You know this thing. You know what is von Mises?
Yes.
You all know this thing.
DE.
Yes,
That's
distortion energy.
Distortion energy.
So, if you want to, if your value of von Mises is more than the half of the yield strength of the material, what you do, you go back to the design, return back some material, add some material, maybe the original drawing or maybe some other place you think that material should be added. Here comes your creativity, and then at the end, only make sure that you don't have any sharp edges. Because if there are sharp edges, for example, if you see in this design, I make a radius over here. Okay, I made the radius over here, radius over here. Because in the design, there are no sharp edges generally in any of the product. If there is a sharp edges, for example, here, if it's an external edge, it won't make any effect. But that internal edge, that can cause, although our analysis says that there is no stress concentration over there, so it's pretty safe, even there, but it can cause something later on in fatigue at the load. Now, we are loading it one time. In fatigue, we load it again and again. Okay, so there is no sharp edge. Understandable?
Yes.
Makes sense? Can you do it by yourself?
Sure. Yes.
Okay? Any question? All right, just have a quick. So what I just said. So I'll provide you the CAD model 2D drawing made by hand. You need to convert it into CAD model. Okay, once you make a CAD model, make sure all the drawings and dimensions are there. Okay. For the assignment, I'll give you a rubric which will define you where your marks are. Okay, there are some marks for the CAD model, some marks for the simulation, some marks for this, and so on and so forth. You can look at it. If I said the diameter should be 35 and you make the diameter 34, you lose marks in CAD. Okay, so it's your job to make it. Once you do this thing, you apply the load points are different for different drawings. Okay, you need to see it in it. I try to add everything over there, but if you're unable to understand, you can discuss, because it's an individual assignment, you can ask me. But before asking, for example, if the question comes to you right now, take 10 hours break. Within 10 hours, you automatically get the answer. But if you don't get the answer within 10 hours, then contact me. Some of the dimensions are not there. They are just deliberately not there to make sure that you're able to make a sketch properly. Okay? Man, if you come to play with the mobile phone, why you are here? Okay? So once you get this drawing, you will be able to make a CAD model. All these files should be in the folder inside the Fusion. You all have the access to the folder?
Yes.
Yes.
Yeah. Can you see?
Yes.
Can you see the folder? Can you see the
Yeah.
folder? Can you see the folder? Can you see the folder?
Yes. Yes.
Can you see your folder?
Yes, yes.
Can you see your folder? Yeah, man, the computer is in front of you. Can you see? Can you see someone else's folder?
Yes. No.
Yeah,
But they did not. But I can see the.
Folder, you can see it, but you cannot go inside.
Yes, but I cannot see what they do. What they do.
Inside the folder, we tried now when I upload in my folder, he go to my folder, but he can't see all my files. He can't see anything.
Just
You can see the folder, but when you go inside, you cannot see anything. Sure?
Yes, sure, I will try.
Alright. Okay. Then the report and the poster,
Okay.
you have to put it back into the same folder. Okay?
Yes.
When you will be able to complete this task?
About 2 weeks time.
2 weeks time from now?
Yes.
after
2 weeks.
No.
Why? Why?
After Eid.
And I don't fight because I'll set the deadline. But I think in even 2 weeks is too far away.
3 weeks.
But, okay. I will send you the deadline and it will not be after Ramadan, for sure. So it's better for you to start. All right. Anything else? So the purpose of asking you to come today, and thank you very much for coming, is just to let you know the workflow. Okay. So you don't know maybe that when I draw it, I don't put the exact dimension and exact this, but I show you the workflow. Do you have any issue in the workflow? Do you have any question, any problem in the workflow? How to do it? No?
This is what you put on YouTube, huh? So we can the video.
Yeah, I can share it with you.
So we can and give you a like.
Just one line? That's not enough.
Subscribe.
Okay. So you understand the workflow? Can you do the workflow?
Yes.
Yes.
Any issue with the workflow? Right now, because it will be very time consuming for me if I go and define the student individually, oh, where to put this, what to do this, okay? So if you have a question, you can ask.
We can't do unless we start doing it ourselves.
Yes.
Yeah, that's what I'm asking. When you do yourself, do you think there is any bottleneck or something which you can,
As such, no, but
all right, at this moment you think that you can do it, confident enough?
we try.
All right, thank you very much. So I'll be here for next 10 to 15 minutes. You can try to do anything, and if you're stuck anywhere, I can comment that.